Namaste everyone. Welcome to second PUC physics class. We were discussing about atoms, right? Bohr's theory. Using Bohr's theory, his quantization rule, we were able to get the radius of the hydrogen electron revolving around the hydrogen nucleus, radius of the hydrogen atom, and energy occupied by the electron in different orbits, namaste, and wave number finally. So all these things we were able to get using Bohr's ideas. And of course the platform is Rutherford's alpha particle scattering model, which gave a correct direction for the model of an atom, that nucleus is very small and dense and atom is large, but most of the portion is empty and all. Okay, so we will assume the expression for energy and we will get a wave number equation again, and then we will move forward, right? So how do we assume, or how did Bohr present his idea? It is very simple, that energy of the electron is due to two ways, two concepts. One is it is in motion, so it will have kinetic energy, and another one is potential energy. So totally every electron should have an energy of E in any orbit, nth orbit. N is quantization number. That means you can have only fixed values. You can fill the n values 1, 2, 3, 4, etc. You can't fill the values half, 0.33, 5.2, something like that. It can have only integral in multiple form. So energy of the electron in the nth orbit is given by minus, total energy is negative, z square. Of course, we are not substituting this in the theory exam, but I am keeping it only for the reason that I want it for the entrance exam. Only for only those students who want to write the entrance exam, better you remember this. Others, okay, no, not needed, because Bohr applied this concept only to hydrogen atom. Minus z square e to the power 4 m divided by 8 epsilon naught square n square h square. Let an electron from the higher energy state E2 to the lower energy state E1, let it jump. And remember, energy state E2 E1 means it is not the second energy or the first energy. It is any higher energy level. So I will represent it as En2 by En1, and I will replace it by En1. Electron is jumping from any higher energy level to the lower energy level. When it jumps, which is one non-radiating orbit, this is another non-radiating orbit, it gives away energy in the form of light, h nu, which is also equal to hc by lambda. So using this concept, let us write what is the difference in energy. Difference in energy is like this: En2 minus En1. Directly we will write it. Okay, today we will cut short one step. You know that when the electron is in the higher energy state, everything is same, z square, because same atom, z square e to the power 4 m h square epsilon naught square 8, only n1 will change. So this En2 can be written as minus z square e to the power 4 m divided by 8 epsilon naught square h square into common thing we will put it inside. What is that common? Common thing we will put it outside the square bracket. The uncommon, that is n. 1 by n1 2. n2, right? Higher energy level. To the lower energy level, minus. To the lower energy level, minus. What is that? n1 2 square, sorry, n2 square minus, again same, z square e to the power 4 m 8 epsilon naught square h square n1 square. Minus sign I have taken it outside itself. So 1 by n2 square minus 1 by n square. Now take this minus sign inside, it becomes easier. En2 from n2 to n1 is equal to minus z square e to the power 4 m divided by 8 epsilon naught square h square, minus sign to the inside. This becomes minus, this becomes plus. 1 by n1 square minus 1 by n2 square. Okay, this energy must be given in the form of radiation. So this should be equal to h nu or hc by lambda. Correct? hc by lambda or h nu. Then what is hc by lambda or h nu? Is equal to z square e to the power 4m divided by 8 epsilon naught square h square into 1 by n1 square minus 1 by n2 square. We will cut short one more step here. What we can do now? Yeah, we want 1 by lambda. What is the wavelength of the light emitted? That is very important because that is what we see in the spectrum. We can calculate the wavelength very easily in the spectrum. Light from a tube containing hydrogen inside and 2 electrodes and accelerated electron from a coil, when it is made to pass through the hydrogen at a very low pressure inside this tube, the electrons will collide with the hydrogen atoms. Hydrogen atoms will absorb the energy from the electron which is liberated from this coil and accelerated, and these atoms, after gaining energy, very soon they will emit that energy in the form of light. What the light you get, what is its wavelength? That is, according to the wavelength we have hydrogen spectrum, right? So its wavelength, you bring this h here, h cube, h gone, c here, so no c, 1 by lambda, this is c. So what is 1 by lambda? So shall I put this, suppose you apply this for hydrogen atom, z is 1 and everything is a constant, e to the power 4, m, c, 8, and if you substitute all these things, what you will get? 1 by lambda is equal to Rydberg constant into 1 by n1 square minus 1 by n2 square. This is called wave number and it is represented by nu bar. This nu has nothing to do with the frequency, of course it is the nu bar is the number of waves in a unit distance, right? That is wave number. So wave number is given by this equation. Already you have seen this in chemistry. Very, very important equation. When as far as problems are concerned, as far as this derivation is concerned. This equation, using this equation, Bohr was able to give a clear explanation for whatever is practically seen in the Bohr hydrogen spectrum. When light from the hydrogen gas, how does the hydrogen gas emit light? Same way. Electrons are made to accelerate inside the hydrogen gas and hydrogen atoms were given energy, they give that in the form of light. That light, when it is made to pass through the prism and the spectrum is observed. Very beautiful spectrum was observed, but which is not visible to the naked eye except a few wavelengths. When the light from the hydrogen is observed, for bare eyes you can see only few lines. And it is a line spectrum. What do you mean by line spectrum? Spectrum is not in the form of continuous colors as we see in the rainbow. Solar spectrum is a continuous spectrum. You can see the light continuously starting from red, red gradually changing into orange, orange gradually changing into another color, blue gradually changing into violet. But it is not so here. You get a particular line, red, then a small amount of darkness, then orange, then yellow, something like this. So it is in the form of bright lines. You go to Google and type hydrogen spectrum, you will get photos. The real photos taken from this, the spectrum of, from the spectrometer. We have an instrument called spectrometer which shows the spectrum of the different wavelengths of light emitted from a hydrogen gas. Okay, so if you observe it and compare it with this one, Bohr was able to give a very clear explanation. Why do you get a particular line here? Why do you get a particular line here? Now, how is this explanation? That is your today's class, right? Okay. Bohr, using the energy level diagram, he puts a, so this is the equation for wave number. And by using the energy equation, E is equal to energy of the electron in any nth orbit is z square. Of course, you have to put z as 1 minus z square e to the power 4m divided by 8 epsilon naught square n square h square. Using this equation, this is the energy, and z equal to 1, n equal to 1, first energy state. If the electron is in the innermost energy state, what is the least energy of the electron? That means most bound to the nucleus. That is minus 13.6 electron volt. You know it. Minus 13.6 electron volt. Okay. This is n equal to 1. What may be the energy of the electron in the next energy state? You can check it. You can substitute the values and check it. Next energy state, put n equal to 2 square. So denominator increases. What about the total energy? It increases actually, because negative values become lesser and lesser. That means actual value of energy is increasing. Minus 13.6 divided by 2 square. This is divided by 1 square. Divided by 2 square. How it will be? divided by 2 square will be minus 3.4 electron volt. Minus 13.6 V divided by 2 square. This is by 1 square. Here N is only changing, atom is same. It is a hydrogen. Z is 1. This is for N equal to 2. What about N equal to 3? It will be here. It is minus 1.51 electron volt. You can check it. Then what else? Next one, I don't calculate. Next one, very close, because the values are decreasing and decreasing, they are becoming closer and closer. 1 by 2 square and 1 by 3 square gap will be larger, but 1 by 3 square and 1 by 4 square gap will be very less. 1 by 4 square and 1 by 5 square gap is much lesser, they come closer and closer, the energy values become closer and closer, and finally it becomes almost continuous. This is N equal to 3, N equal to 4, am I right? 1, 2, 3, 4, and this is N equal to 5, this is N equal to 6, N equal to infinity. And if you go on like this, 0 electron volt. These are the different energies possessed by an electron. Of course, I have not written all the energies. But from here onwards, it appears to be continuous, but still it is having definite energy. Now, but the values are very close so that it appears to be continuous, but it is not continuous energy. It is a different amount of energy, discrete values of energy. Now, Bohr says, and the spectrum of hydrogen, it will be like this. If you pass the light through a prism and observe the light emitted by the hydrogen spectrum, after passing through the prism in a spectrometer, there is a separate instrument with the telescope and all, and you can see the spectrum. Spectrum contains lines like this. Hydrogen spectrum is a line spectrum. Then after some lines, you don't see any lines. Then again another set of lines. Another set of lines. Of course, all the lines you can't see. For your bare eyes, you can see some lines in this spectrum. So here a set of lines were observed like this, and these set of wavelengths were called by some names like this: Lyman series, Bohrs series, Lyman, Bohrs, Passion, bracket, fund, and all. Now, how this spectrum is observed? You see the spectrum in computer, and you will get this, and you will Google images. You will get many pictures. You go to images, plenty of pictures. So that's how it observed, and it is like in the form of lines, not like continuous colors, like in a rainbow, right? It is in the form of lines. Now, Bohr gives the explanation like this: electron is in the ground state, say, it absorbs energy, goes to any of the higher orbits. When it jumps, it may give different values of energy depending on which is the higher energy state and which is the lower energy state. Depending on the higher and lower energy state, it gives the energy. Suppose an electron jumps to the ground state itself, N equal to 1, from any of the higher energy state, from 2 to 1, 3 to 1, 4 to 1, infinity to 1, then it is coming under Lyman series. That is why you get a set of wavelengths here, and this is Lyman series. What is Lyman series? Lyman series is a series obtained, or the set of wavelengths in the hydrogen spectrum obtained when the electron jumps from any of the higher orbits to the lower orbits, right? I'll write this new bar formula here so that explanation becomes continuous. 1 by lambda is equal to Rydberg constant into 1 by n1 square minus 1 by n2 square. Now, if n1 lower orbit is 1 and n2 is equal to 2, 3, 4, 5, etc., any of the higher orbit, if n1 is equal to 1 and n2 is equal to 2, 3, 4, 5, any value up to infinity, then it is called Lyman series. What is the first wavelength that you get in the Lyman series? Of course, if it is from least wavelength to the most wavelength like this, okay, wire is getting, I have to turn along with the wire. If this is the least wavelength and the most wavelength, remember these are all energies. So while studying for entrance exam, you should be very careful here. Or even in the theory problem, these are the energies. When the electron jumps from 2 to 1 in the Lyman series, any jumping, any transition of electron, when any emission of electron energy, when it jumps to the lowermost energy level, n1 equal to 1, corresponds to Lyman series. When it jumps here, when it jumps here, these are all Lyman series. So light is emitted. Okay, the last one infinity to 1, correct? Last one I will indicate. You see, this is least energy, most wavelength. Can you identify? This energy difference is least. This is more. This is the most energy, least wavelength. That means this one is this wavelength. Suppose lambda is increasing as you move like this. Okay, this is a least wavelength. Say this wavelength is least and this wavelength is most. Then wavelength is increasing, lambda increasing in this direction. Okay, I will write it like this. This is least wavelength and this is most wavelength. Now which is the least wavelength? Most energy is equal to hc by lambda. Most energy least wavelength. Most energy least wavelength. So that is this one. This first line. And next one like this. What is this one? That is this last line, right? This last colored line represents the energy emitted or the wavelength emitted when the electron jumps from 2 to 1, this one. That's how we can identify. So when the electron jumps from any of the higher orbit to the first orbit, the wavelength emitted come under Lyman series. And this cannot be seen in your naked eyes. You have to use separate instrument to see that, because this is in the ultraviolet region. This Lyman series in the UV region. Okay. Sir, what is the guarantee that all the electrons when they gain energy go to the higher energy band and jump to the first energy state only? Okay, there is a chance that they may jump to the second energy level from 3 to 2, 4 to 2, 5 to 2. So if the electron jumps from any of the higher energy level, N1 is equal to 2 from any of the higher energy level, 3, 4, 5, 6 up to infinity. Then it is called Bohrs series. What is Bohrs series? Electron jumps from and it emits light and its wavelength is given by this. You have to suppose the electron jumps from 3 to 2. Put N1 equal to 2, N2 equal to 3. You will get the wavelength. And you know the Rydberg constant value. Value of Rydberg constant is for hydrogen 1.09 into 10 to the power 7 meter to the power minus 1, because it is 1 by lambda. Okay, if it jumps from the higher energy level, third orbit, say second orbit, fourth to second, fifth to second, last one, infinity to second. Then this is Lyman, this is Bohrs. And Bohrs series, a part of the Bohrs series is in ultraviolet region and a part of the Bohrs series is in visible region. So visible and ultraviolet. So visible, some of the lines are visible here, and ultraviolet. Which is visible? The first line is visible, this one. Second line is visible, of course, from this end, because this is least energy, most wavelength. So this is visible, and this is called H alpha line. We will name it H alpha, and this is called H beta and H gamma, this one. What is H alpha line? H alpha line is the wavelength obtained when the electron undergoes transition from 3 to 2. H beta line is the wavelength obtained when the electron undergoes transition from 4 to 2. And H gamma is the transition from 5 to 2. 5 to 2 means 5 is N2, N1 is 2. So when the electron undergoes transition from third orbit to second, fourth orbit to second, we see the visible lines. That's why they are named separately as H alpha, H beta and H gamma. You can see them, but rest of the things again they go under ultraviolet range. You can't see them. So if the electron jumps from any of the higher orbit to the third orbit, like this, and the last one, this one, what is this called? Lyman Bohrs Paschen series. P-A-S-C-H-E-N. So what is Paschen series? Paschen series is the set of wavelengths obtained in a hydrogen spectrum when the electron in the hydrogen atom jumps from any of the higher orbit corresponding to 3, 4, 5, 6, etc. to the 4, 5, 6, etc. to the third energy level. That is called Paschen series, and this comes under infrared region. can't be seen. This is in the infrared region, it is higher wavelength again. So you can describe it like this. So whatever Bohr explained and whatever is seen practically exactly matched each other. And one more thing, the wavelength calculated practically by observing the hydrogen spectrum. What is this wavelength? There are different methods of calculation. And the wavelength obtained by using the Bohr's results, that is wave number result, substituting the values here, Rydberg constant and all, practically they were found to be the same, almost same, within the limits of practical errors. So that gave another boost to Bohr's theory, because Bohr theory was accepted. So the thing is here, Bohr was able to explain the different spectral series of hydrogen atom, and which were found to be true, and the wavelength calculated using the practical value and Bohr's formulas were found to be correct. But of course, you can explain it further. What is the next series? Paschen, Lyman, Balmer, Paschen, bracket. What is bracket series? If the electron jumps from any of the higher orbit to the fourth orbit, right? 5 to 4, 6 to 4, 7 to 4, like that. So you can continue it. Now, but Bohr was not able to explain the intensity of the spectral line. What do you mean by intensity of the spectral line? If you observe the spectrum carefully, then you will find that some of the lines are very bright in this. Some of the lines are not so much brighter. The intensity of some particular lines was very bright, and he couldn't explain this. So that is one drawback of Bohr's theory. If you are asked to write the drawbacks of Bohr's theory, limitations of Bohr's theory, first one you have to write, Bohr's theory is, Bohr's theory couldn't explain the intensity of the spectral lines in the hydrogen atom. Why some lines are brighter and why all the lines are not equally brighter? Some are less brighter. And second one, fine structure of spectral lines. What do you mean by fine structure of spectral lines? If these wavelengths are observed in a very good resolution microscope or telescope, or spectrometer, we are using a high resolution spectrometer, when the hydrogen spectrum was observed, it is found that this wavelength, now I say that this wavelength, for example this one, this is obtained when the electron jumps from second orbit to the first orbit, isn't it? But when this line is observed, that particular wavelength is observed using a very strong spectrometer, it is found that that is not a single wavelength, it is a collection of many wavelengths. That is what you call fine structure. It is made up of so many wavelengths, and collectively it appears to be a single color, single wavelength, but it is made up of multiple colors, multiple wavelengths. So fine structure means the wavelength corresponding to a single transition in Bohr's orbit, Bohr's theory. So for example 2 to 1 is not a single wavelength, it is a collection of wavelengths. And this, why this splitting of, or not splitting, why these components in these wavelengths are seen? The explanation of the fine structure of the hydrogen spectrum, which is practically observed, was not satisfactorily explained by Bohr's theory. Third one, so fine structure was not explained because every wavelength is a collection of many wavelengths. Third one, Bohr's theory can be explained only to hydrogen and hydrogen-like atoms. It cannot be explained to or applied to complicated atoms. So you can apply to only hydrogen-like atoms, not for complicated atoms. So in this way, we have some limitations of Bohr's theory. One is it cannot be applied to other than hydrogen-like atoms. It cannot explain the fine structure of spectral lines, and it couldn't explain the intensity of the spectral lines. So something like this, we have some drawbacks, and there are many drawbacks like and of course these drawbacks were successfully answered by somebody else later. So all those things, we need not worry about all those things now. But this derivation is very important. And one more thing we have in between in that, very small term, that is what about electron when it moves in a circular orbit with such a high speed? You substitute the values for velocity of the electron in the first orbit, for example. Z square divided by 2 epsilon naught nh, we get formula, velocity is equal to Z square by 2 epsilon naught nh. So what you have to do is, you just write all those formulas, big formulas, minus Z square e to the power 4m divided by 8 epsilon naught square n square h square. Then radius is epsilon naught n square h square divided by pi m Z square. Velocity is what is velocity? Epsilon naught ns divided by pi mz square. So all those formulas, write it and put it in the on a wall and try to see them, recall them every now and then. Otherwise, you won't be able to remember it till the examination. You know that electron, so take that formula for velocity, epsilon naught nh divided by pi mz square, isn't it? Velocity is epsilon naught nh divided by pi mz square. Take that formula, substitute all the values, epsilon naught, n take it as 1, h pi mz square, okay, all those things. Z is 1. Find out the velocity of the electron in the first orbit. It is tremendous high. It is revolving around the nucleus with a very high speed. Sir, when the electron moves with such a high speed, what about de Broglie's wavelength? It's a particle moving with a high speed. Doesn't it emit, or won't it behave like a wave? Now we will go back to that. Because this theory, all the theories finally they should match each other. De Broglie said that any moving matter must be associated with a wave. And that is not this wavelength. Remember, this wavelength is electromagnetic radiation. A particle behaving like a wave, and we treat it as a wave and give a wavelength for it, that is different. That is not this wavelength. So, if you take an electron moving around the nucleus in a circular orbit, de Broglie said that the wavelength of the matter wave, that is electron, its wavelength and the circular orbit length, what you call circumference, they must be related. They must be equal, or in some other term, or they must be an integral multiple. For example, they must have an integral multiple relation. That's what I want to say. I'm not getting correct words today, I don't know. So, if an electron is revolving around the nucleus in the circular orbit, that electron of mass m, when it moves with a certain speed v, it has a momentum. Lambda is equal to h by p, you know this. And this is also a particle. Apply the de Broglie wavelength here. If it is behaving like a wave, and if it is having a, if it is acting like a electromagnetic radiation, and of wavelength lambda is equal to h by p, then my question is, or his explanation is, not my question, his explanation is, the radius, the circumference of the circular path and the de Broglie wavelength, they must be related by an integral multiple. That means because everything is an integral multiple. If you have the first orbit here, next orbit should be of size 2 square times. Next orbit should be 3 square times, because there is a direct relation. It should be an integral multiple. Either square of the integral multiple or inverse proportional to integral multiple, whatever it is. Now, he says like this: suppose an electron moves around the nucleus in the circular orbit, then if you calculate that de Broglie wavelength, and if you write a waveform like this, then de Broglie says that by the time you come here, the exact wavelength should complete. You can't have half. That means the circumference the circumference of the circular orbit and the wavelength must be related like this, where n is a quantum number again. The circumference of the circular orbit must be equal to n times the de Broglie wavelength. Here you see how many waves I have drawn. 1 wave, 2 wave, 3, 4, 5, 6. I have not completed it then. 1, okay, I will start from here. 1, 2, 3, 4, 5. Okay, I'll complete it because it shouldn't be a half wave here. The circumference of the circular path, okay, it was completed. 1, 2, 3, 4, 5, 6. It should be like this. The circumference of the circular path and the wavelength of the matter wave must be related like this. So circumference must be an integral multiple of the wavelength. That's what I was about to say from 5 minutes. I am struggling for words. Circumference is equal to n times the wavelength. Sir, if n equal to 1, how do you write the wavelength? It is very difficult. If it is the first orbit of the electron around the nucleus, how do you represent the one wavelength completely with the circumference? It is very difficult, right? It should start from here and very difficult. You can't do that. So second, third of course can be shown. Suppose it is equal to 3 lambda, third orbit. If the electron is in the third orbit, then you can show it 1, 2, 3. It should get completed here, right? 1 wave, 2 wave, and of course this is okay, a little bit more, whatever it is. Okay, well, like this, 3 waves. Here we have shown 4 waves, so it is the 5th orbit. So when the electron revolves around in different orbits, it will have different speeds, it will have different momentum, different de Broglie wavelength, and the de Broglie wavelength n times must be equal to the circumference of the orbit, circular orbit. In such a case, if the electron is in the nth orbit, so shall I write it as circumference of the electron orbit is 2 pi r and must be equal to n lambda, right? And you see, using this idea, de Broglie was able to arrive at the Bohrs rule. Bohr says if an electron has to revolve around the nucleus in a particular orbit, there is a condition that in that path, in that orbit, the orbital angular momentum L must be equal to nh by 2 pi, right? Angular momentum moment of momentum must be equal to nh by 2 pi. This is what Bohr said. De Broglie, by assuming this, was able to come at that or reach to this conclusion. Now substitute for this lambda. Lambda is equal to h by 2 pi. What is lambda? Lambda is equal to 2 pi r by n. Shall we substitute for this? Lambda is equal to 2 pi r by n, that is equal to h by p. So we will take this formula. I will write it here. Lambda is equal to h by p. Both are the assumptions of de Broglie. Lambda is 2 pi r by n, h by p. H by m we will write, right? Then what I will get? mvr, bring this here. mvr must be equal to n h by 2 pi. Did we come across this one again? Right? We got it, right? So using de Broglie's assumption, he could arrive at, and he could arrive at the Bohr's quantization rule. How did Bohr assigned circular orbits for the electron? How it was assumed here. So just a very simple one, if it is asked in the examination, using de Broglie's hypothesis, arrive at the Bohr's postulate. Bohr's postulate is angular momentum must be equal to nh by 2 pi. That is Bohr's postulate. You have to arrive at this using de Broglie's hypothesis. De Broglie says that any moving particle or any matter should be associated with a wave which is given by lambda is equal to h by p, and according to him the circumference of the circular orbit must be equal to the n times the de Broglie wavelength, and circumference is 2 pi r which is equal to n lambda. 2 pi r by n is equal to lambda. Put that lambda here, 2 pi r by n is equal to h by mv, and bring mvr together. Mvr is equal to nh by 2 pi. That is the assumption of Bohr. Sorry, not assumption, that is the Bohr's postulate about hydrogen spectrum. Okay, so, and one more drawback, a limitation of Bohr's theory is it has not explained the distribution of the electrons in different shells and different orbits. That is one more, I just suddenly remembered it. So this is about atoms. Chapter is over. Okay, atoms is also over. So we finished optics, ray optics, wave optics, dual nature of matter, and now it is atoms. Now is nuclei, again a small chapter. We will finish it, another semiconductor, another new small chapter, and that one textbook is over, part 1, part 2. Part 2 will be over within 2 chapters, and we will come up with some problems here, especially with this formula. Very, very important formula. You will get simple problems under this, either derivation or this one. So hope you will follow this. Today we will end up with this one. So thanks for watching my class. Study all the derivations. Atoms is a very important chapter. Don't forget it. And you have to carry these derivations till the end of the year, right? So I don't know when will be the end of the year, because we haven't seen the beginning of the year itself. So definitely it will open on one day, and we will have to live with corona after a few days. But we have to take care of our health. That is our responsibility. We can't blame anybody else. We must be very careful, and you have to use all these classes. You must use all these classes, otherwise you will be in a trouble later. So I have found so many students using this, but so many students are wasting their time, right? But you will have to pay for that later. So after the lockdown and all these things are getting lesser and lesser, all the teachers will start coming to the college again, and you will have more classes in the coming days. Okay, so thanks for watching my class. One more thing is, after the completion of this chapter, I will give you some entrance exam classes on dual nature as well as atoms, right? So during that time I won't be having any theory class. You will get some entrance exam class. So use them so that it will be a platform to go forward. Otherwise, all of a sudden, if you attend a crash course class, this class and that class, you can't cope up with that. It becomes very difficult to adjust with all those things. So try to use them. Okay, thanks for watching, and we will meet in the next class with problems. Okay, thank you.